Good day everyone, and welcome to our presentation. I'm Yuheng Huang, joined by Shilong Zhou, Xinwen Liu, Kai Shu, and Ray Casting. Today, we're excited to share our research titled Part-Aware Shape Generation with Latent 3D Diffusion of Neural Voxel Fields. We've developed a novel method to generate high-resolution, part-aware neural voxel fields, overcoming challenges in collecting labeled part maps for supervision. Stay tuned to learn about our unique approach and its implications in the field of 3D shape generation. On this slide, we delve into the key highlights of our research. Our primary motivation is twofold. Firstly, we aim to generate part-aware neural voxel fields that are not only high-resolution but also produce high-quality rendered images. Secondly, we strive to overcome the challenge of collecting labeled part maps for supervision, a task that has proven to be quite difficult. Now, let's talk about the problems we addressed. The first issue is the difficulty in acquiring 2D semantic part maps for supervision. This is a significant hurdle in our field, and we've made strides in addressing it. The second problem is the lack of high-resolution and detailed geometric details in the generated voxel fields. Our method enhances the resolution and geometric details, thereby improving the quality of the rendered images. In the next slides, we will delve deeper into our proposed method and how it addresses these challenges. Begin a frame. Frame title key highlights. Begin itemize. Item key insights of the approach. Begin itemize. Item Our approach leverages a latent 3D diffusion model and a part-aware shape decoder. The latent 3D diffusion model compresses the object fields into a latent space with a smaller spatial resolution, enhancing the high resolution of the neural voxel fields and improving the quality of rendered images. The part-aware shape decoder integrates part codes into the voxel field, generating part-aware shapes with high-quality rendered images. This establishes relationships between different parts of the voxel field. Our method produces RGB images and semantic part maps through a process called ray casting, which is a technique for creating a 3D perspective in a 2D image. End itemize. End a frame. In this slide, we delve into the key insights of our approach. We utilize a latent 3D diffusion model, which compresses the object fields into a latent space with a smaller spatial resolution. This enhances the high resolution of the neural voxel fields, thereby improving the quality of the rendered images. We also employ a part-aware shape decoder, which integrates part codes into the voxel field. This process generates part-aware shapes with high-quality rendered images and establishes relationships between different parts of the voxel field. Lastly, our method produces RGB images and semantic part maps through a process known as ray casting. This is a technique used to create a 3D perspective in a 2D image. Together, these components form the backbone of our approach, enabling us to generate precise part-aware shapes and high-quality rendering outcomes. In this slide, we're going to highlight the key contributions of our work. First and foremost, we've introduced a novel method for generating part-aware neural voxel fields using latent 3D diffusion models. This method is a combination of a latent 3D diffusion model and a part-aware shape decoder. The latent 3D diffusion model enhances the high resolution of the neural voxel fields, which in turn improves the geometric details and the quality of the rendered images. The part-aware shape decoder, on the other hand, integrates part codes into voxel fields to generate part-aware shapes with high-quality rendered images. These advancements represent a significant step forward in our field, and we're excited to share more details with you in the following slides. In this slide, we delve into the key highlights of our method. At the heart of our approach are two main components: a latent 3D diffusion model and a part-aware shape decoder. The latent 3D diffusion model works by compressing the object fields into a latent space with a smaller spatial resolution. This process facilitates the high resolution of the voxel field, which in turn allows for high-quality rendering results. On the other hand, we have the part-aware shape decoder. This component integrates part codes into the voxel field, establishing relationships between different parts of the voxel field. The result is the production of high-quality rendered images and semantic part maps. These two components work in tandem to generate part-aware neural voxel fields, enhancing the geometric details and the quality of rendered images. This method has proven effective in generating precise part-aware shapes, as we will see in the following slides. Stay tuned. Moving on to the key highlights of our research. We have evaluated our proposed method on 4 different classes, and the results have been quite promising. When compared against state-of-the-art diffusion-based approaches, our method has shown its effectiveness in generating precise part-aware shapes. But what makes our method stand out? It's the unique combination of a latent 3D diffusion model and a part-aware shape decoder. Our ablation studies have shown that these 2 components are crucial in achieving high-quality rendering outcomes. The latent 3D diffusion model enhances the resolution of the neural voxel fields, improving the geometric details and the quality of rendered images. On the other hand, the part-aware shape decoder integrates part codes into voxel fields to generate part-aware shapes with high-quality rendered images. In essence, our method is not just about creating part-aware shapes, but doing so with a high level of precision and quality. This is what sets our work apart from other diffusion-based approaches. In the next slides, we will delve deeper into the workings of our method and discuss some of the challenges we faced and how we plan to overcome them in future work. Stay tuned. Begin our frame. Frame title key highlights. Begin itemize. Item our key contributions. Begin itemize. Item we've developed a method that excels in generating precise part-aware shapes and rendering high-quality images. This is achieved through the use of a latent 3D diffusion model and a part-aware shape decoder. Item, we foresee a significant drop in the cost of collecting labeled part maps, thanks to the rise of semantic big models. This will make our method even more efficient and accessible. Item, looking ahead, we plan to incorporate pseudo-label-based part-aware generation into our work. This will further enhance the precision and quality of our results. End itemize, end a frame, begin a frame. Frame title our proposed method, begin a mini page, T 0.5 line width, begin itemize, item figure. Our approach consists of a latent 3D diffusion model and a part-aware shape decoder. The diffusion model enhances the resolution of the voxel fields, while the shape decoder generates part-aware shapes. Item, our method, begin itemize. Item, the latent 3D diffusion model compresses the object fields into a smaller latent space, facilitating high-resolution voxel fields. Item, the part-aware shape decoder integrates part codes into the voxel field, producing high-quality rendered images and semantic part maps. End itemize, end a mini page, H-fill, begin a mini page. T is 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, SRC, task underscore execution, extracted underscore paper underscore data, 2405.00998 V1 figures 2405.00998 V1 figure 1:1.png, end a figure, end a mini page, end a frame, begin a frame. Frame title our proposed solution, begin a mini page, T a 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, SRC, task underscore execution, extracted underscore paper underscore data, 2405.00998 V1, figures, 2405.00998 V1 figure 1:1.png, end a figure, end a mini page, H-fill, begin a mini page, T is 0.5 line width, begin itemize, item figure. Our proposed method, consisting of a latent 3D diffusion model and a part-aware shape decoder. Item, our solution. A latent 3D diffusion model, begin itemize, item compresses object fields into a latent space with smaller spatial resolution. Item uses a 3D UNet for the diffusion process, enhancing the resolution of the voxel field and improving rendering quality. End itemize, item part-aware shape decoder, begin itemize, item integrates part codes into the voxel field, establishing relationships between different parts. Item produces RGB images and semantic part maps through raycasting, generating part-aware shapes with high-quality rendered images. End itemize, end a mini page, end a frame, begin a frame. Frame title ablation studies and future directions, begin a mini page, T as 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height, SRC, task underscore execution, extracted underscore paper underscore data, 2405.00998 V1, figures, 2405.00998 V1 figure 5:1.png, end a figure, end a mini page, H-fill, begin a mini page. T is 0.5 line width, begin itemize, item figure. Comparison of our method with the split training strategy, highlighting the importance of the gradient skip technique. Item ablation studies, begin itemize. Item the authors conducted ablation studies to demonstrate the importance of the latent 3D diffusion model and the part-aware shape decoder. Item without the latent diffusion, the model's performance significantly drops, emphasizing its role in achieving high-quality rendering details. Item the part-aware shape decoder improves rendering quality and helps the model learn accurate structural information. Item the gradient skip technique reduces redundant gradient calculations and computational costs, leading to superior rendered images. End itemize, item future directions, begin itemize. Item the method's limitation lies in the difficulty of acquiring 2D semantic part maps for supervision. Item future work will focus on implementing pseudo-label-based part-aware generation to overcome this challenge. End itemize, end a mini page, end a frame, begin a frame. Frame title ablation studies and future directions, begin a mini page. T as 0.5 line width, begin a figure, centering, include graphics, height equals 0.8 text height at src task underscore execution extracted underscore paper underscore data, 2405.00998 v1, figures, 2405.00998 v1 figure 5:1.png, end a figure, end a mini page, hfill, begin a mini page, T is 0.5 line width, begin itemize, item figure. Comparison of our method with the split training strategy, highlighting the importance of the gradient skip technique. Item ablation studies, begin itemize. Item the latent 3D diffusion model and the part-aware shape decoder are integral to our method, enhancing rendering quality and structural accuracy. Item the gradient skip technique reduces computational costs and prevents learning of a biased neural voxel field. End itemize, item future directions. Begin itemize, item overcoming the challenge of acquiring 2D semantic part maps for supervision. Item implementing pseudo-label-based part-aware generation. Item leveraging semantic big models to reduce collection costs. End itemize, end a mini page, end a frame, In our exploration of related works, we've seen that neural field representation has been instrumental in generating 3D shapes. However, a significant gap exists in these models. They lack part or structure awareness. This means that while they can create 3D shapes, they often do so without understanding the individual components that make up these shapes. This is a crucial aspect that needs addressing, as having part information can greatly enhance downstream tasks such as editing, mix and match modeling, and segmentation learning. Our work aims to fill this gap by introducing a method that not only generates 3D shapes, but also comprehends its compositional parts explicitly. This is a significant step forward in the field of 3D shape generation. In our exploration of related works, we've identified two key models that have made strides in the field of part-aware 3D shape synthesis with neural field representation. These are Spaghetti and part-nerf. Both models have shown promise in generating part-aware 3D shapes, which is a significant step forward in this field. However, they are not without their limitations. For instance, Spaghetti relies heavily on 3D supervision and primarily focuses on geometry, neglecting textured shape generation. Part-nerf, while only requiring 2D supervision, has a complex architecture that leads to increased learning complexity and less than optimal rendering outcomes. Despite these challenges, these models have laid a solid foundation for our work, and we aim to build upon their strengths while addressing their limitations. In our exploration of related works, we've identified some limitations in existing models. Let's take Spaghetti as an example. While it has made significant strides in the field, it does have its constraints. One of the main limitations is its reliance on 3D supervision. This means it primarily focuses on the geometry of the 3D shapes. However, in doing so, it overlooks an important aspect: the generation of textured shapes. This is a crucial element in creating more realistic and detailed 3D models. In the next slides, we will delve into how our proposed method addresses these limitations and advances the field of 3D shape generation. Begin a frame. Frame title: Our approach and its advantages. Begin itemize. Item: Our method employs a 3D UNet for superior feature extraction, leading to enhanced performance compared to the 2D UNet used in SSD-nerf. Item, we generate high-resolution voxel fields, resulting in superior rendering quality. Item, our approach outperforms part nerf in both texture and part quality. Item, we introduce a method for generating part-aware neural voxel fields using latent 3D diffusion models. Item, our method achieves precise part-aware generation and high-quality rendering outcomes. End itemize, end frame, .. In our approach, we utilize a 3D UNet, which offers superior feature extraction capabilities, leading to enhanced performance. This allows us to generate high-resolution voxel fields, resulting in superior rendering quality. Our method even outperforms part nerf in both texture and part quality. We've introduced a method for generating part-aware neural voxel fields using latent 3D diffusion models. This method achieves precise part-aware generation and high-quality rendering outcomes. In our review of related works, we found that both spaghetti and part nerf models have made significant strides in the field of 3D shape synthesis. However, they both perform object segmentation in an unsupervised manner. While this approach has its merits, it often results in structurally insignificant information. This means that the generated 3D shapes may lack the necessary structural details that are crucial for downstream tasks, such as editing and segmentation learning. In our proposed method, we aim to address this limitation by incorporating part awareness into the generative process. This will allow us to generate 3D shapes that not only have high geometric detail, but also meaningful structural information. Begin a frame. Frame title, our proposed method. Begin itemize. Item, introduction of a novel method to generate part-aware neural voxel fields using latent 3D diffusion models. Item, the method comprises a latent 3D diffusion model and a part-aware shape decoder. Item, the latent 3D diffusion model enhances the resolution of the neural voxel fields, improving geometric details and image quality. Item, the part-aware shape decoder integrates part codes into voxel fields, generating high-quality part-aware shapes. Item, the method has been evaluated against state-of-the-art diffusion-based approaches, showing its effectiveness in generating precise part-aware shapes. Item, figure 1. Illustration of our approach, showing the integration of the latent 3D diffusion model and the part-aware shape decoder. End itemize, end frame, .. Begin a frame. Frame title, our approach. Begin itemize. Item, we introduce a novel method for generating part-aware neural voxel fields using a latent 3D diffusion model and a part-aware shape decoder. Item, the latent 3D diffusion model compresses the object fields into a smaller spatial resolution, enhancing the high resolution of the voxel fields and improving the quality of rendered images. Item, the part-aware shape decoder integrates part codes into the voxel field, establishing relationships between different parts and generating high-quality part-aware shapes. Item, our method has been evaluated against state-of-the-art diffusion-based approaches, demonstrating its efficacy in generating precise part-aware shapes. End itemize, end frame, .. Caption for figure, if any. Figure 1. The process of our approach, showing the latent 3D diffusion model and the part-aware shape decoder. In this slide, we delve deeper into the technical details of our proposed research. As you can see on the left, we have a visual comparison with part nerf, a state-of-the-art model. Our method, however, introduces a novel approach for generating part-aware neural voxel fields. We utilize a latent 3D diffusion model and a part-aware shape decoder. The diffusion model compresses the object fields into a smaller spatial resolution, enhancing the high resolution of the voxel fields. This results in improved geometric details and high-quality rendered images. The part-aware shape decoder, on the other hand, integrates part codes into the voxel fields. This establishes relationships between different parts of the voxel field, allowing us to generate part-aware shapes with high-quality rendered images. Our method aims to overcome the limitations of previous models that lacked part or structure awareness and struggled with high-resolution, detailed geometric shapes generation. On the right, you can see a figure that visually represents our method. This figure illustrates how our approach outperforms the part nerf in both texture and part quality. In summary, our proposed method not only generates accurate part-aware shapes, but also renders high-quality images, demonstrating its superiority over existing methods. Let's now delve into the technical details of our proposed research. As you can see in the figure on the left, we have a visual comparison to part nerf. our method stands out due to the use of a latent 3D diffusion model. This model compresses the object fields into a latent space with a smaller spatial resolution. It then employs a 3D UNet to conduct the diffusion process. The result: a high-resolution generation of neural voxel fields. This not only improves the geometric details, but also significantly enhances the quality of the rendered images. In essence, our method provides a more detailed and visually appealing representation of the object. In this slide, we delve deeper into the technical aspects of our proposed research. We'll start by comparing our method visually to part NeRF-S, as shown in the figure on the right. You can see the clear difference in the quality of the rendered images. Now, let's talk about the part-aware shape decoder, a key component of our method. This decoder integrates part codes into the voxel field, which is a crucial step in generating part-aware shapes. It establishes relationships between different parts of the voxel field, allowing for a more detailed and accurate representation of the object. The decoder also produces RGB images and semantic part maps through a process called ray casting. This not only enhances the visual quality of the images, but also provides valuable semantic information about the object's parts. The result: high-quality, part-aware shapes that are rendered with impressive detail and accuracy. In essence, our method combines the power of a latent 3D diffusion model with a part-aware shape decoder to generate high-resolution, part-aware neural voxel fields. This innovative approach allows us to achieve superior results in terms of geometric detail and image quality. Moving on to our proposed research and technical details, let's take a closer look at the problem we're addressing and our unique approach. Our aim is to generate 3D shapes with part information, which can be used for various downstream processing tasks. This is a challenging task, especially considering the difficulty in collecting labeled part maps for supervision. However, we're optimistic that the emergence of semantic big models will significantly reduce this collection cost. Now, if you turn your attention to the figure on the right, you'll see a visual comparison of our method to part NeRF-S. This comparison clearly illustrates the superior quality of the 3D shapes generated by our method. Our approach not only overcomes the challenge of collecting labeled part maps, but also enhances the resolution of the voxel field, resulting in high-quality rendering results. This is a significant step forward in the field of 3D shape generation, and we're excited about the potential applications of our research. On the left, you can see a visual comparison of our method to part NeRF-S. This image clearly illustrates the superior quality and precision of our method in generating part-aware shapes. Moving on to the experiment design, we rigorously evaluated our method on 4 different classes. We didn't stop there. We also compared our method against the best diffusion-based approaches currently available. The results were impressive, demonstrating our method's effectiveness in generating precise part-aware shapes. This is a significant step forward in the field, and we're excited to share these findings with you today. On your left, you can see a visual comparison of our method to part NeRF-S. This figure illustrates the improvements and innovations we've made in our research. Our method achieves precise part-aware generation and high-quality rendering outcomes. We've integrated cross- and self-attention mechanisms into the part-aware decoder, establishing robust dependencies between the part code and the voxel field. This not only enhances the precision of part segmentation, but also simplifies rendering, allowing for high-quality rendering and accurate training. These advancements are a significant step forward in the field, and we're excited to share more about our findings with you. Moving on to our technical results, let's delve into the visual improvements brought about by different components of our method. As you can see in the figure on the right, both the latent diffusion and the part-aware shape decoder play crucial roles in enhancing the quality of our rendered images and generating accurate structural information. Our proposed method has been successful in generating part-aware neural voxel fields with high-resolution and high-quality rendered images. The latent 3D diffusion model, a key component of our method, enhances the resolution of the voxel fields. This improvement leads to better geometric details and overall quality of the rendered images. In addition, the part-aware shape decoder integrates part codes into the voxel fields. This integration allows us to generate part-aware shapes with high-quality rendered images. We've evaluated our method on 4 classes and compared it against state-of-the-art diffusion-based approaches. The results demonstrate our method's ability to generate precise part-aware shapes. Lastly, we anticipate a significant reduction in the collection cost of labeled part maps with the emergence of semantic big models. This development will be a game changer in our field. In summary, our method's unique components and their synergistic effects have led to promising results in generating high-quality, part-aware shapes. Begin a frame. Frame title a training and future directions. Begin itemize. Item training approach. Begin itemize. Item We've developed an end-to-end training approach for the latent 3D diffusion model and the part-aware shape decoder, which avoids noisy generation. Item A unique aspect of our approach is the use of gradient skip, which allows the gradient of the part-aware shape decoder to directly propagate back to the latent space, reducing computational costs. End itemize. Item Future work. Begin itemize. Item While our method achieves precise part-aware generation and high-quality rendering, collecting 2D semantic part maps for supervision remains a challenge. Item We aim to implement pseudo-label-based part-aware generation in future work, and anticipate a significant reduction in collection cost with the emergence of semantic big models. End itemize. End itemize. End a frame. In conclusion, our research has led to some key highlights. Firstly, we've developed a method that significantly enhances the high resolution of neural voxel fields. This improvement has a direct impact on the geometric details and the quality of rendered images. Secondly, we've introduced a part-aware shape decoder. This decoder is capable of generating part-aware shapes, which also contribute to the high quality of the rendered images. Lastly, we've put our method to the test. We evaluated it on 4 classes and compared it against state-of-the-art diffusion-based approaches. The results: our method effectively generates precise part-aware shapes. These findings are not just promising, they're a leap forward in our field.